Welcome back to QHSE Talks, where we translate safety knowledge into practical, defensible decision-making for today's safety professionals. In this episode, we are stepping into Chapter 5 of David Yates titled Math Review. And right from the outset, it's important to be very clear about what this chapter is and what it is not. This is not a return to classroom mathematics, and it is not about memorizing equations in isolation. Chapter 5 exists for one reason: to ensure that safety practitioners can confidently apply math when it actually matters, under exam conditions and in real operational environments. Every serious safety calculation depends on this foundation. Ventilation flow rates, noise exposure assessments, electrical safety limits, spatial clearances, rigging angles. None of these are judgment calls alone. They are quantitative decisions, and when the math behind them is flawed, the safety outcome is compromised, regardless of intent or experience. What the source material makes very clear is that ASP and CSP exams do not test math as a standalone discipline. They test your ability to use math correctly inside safety formulas, often under time pressure, using an on-screen calculator, and with no room for procedural mistakes. That's why this chapter revisits fundamentals like order of operations, signed numbers, exponents, absolute values, logarithms, and scientific and engineering notation. These are not basic topics in practice because small errors here cascade into major miscalculations downstream. The chapter also places strong emphasis on algebraic transposition, the ability to isolate variables cleanly and accurately. Whether you are solving the ventilation equation for airflow, rearranging Ohm's law in an electrical scenario, or working backward from a known exposure limit, this skill is non-negotiable. You are expected to move fluently between forms of an equation without hesitation. And then there is geometry and trigonometry. Areas, volumes, right triangles, sine, cosine, tangent, presented not as abstract theory, but as applied tools. These calculations show up in ladder angles, ramp inclines, sling tensions, duct sizing, and physical layout evaluations. This is math that safety professionals actually use. At its core, Chapter 5 does something essential. It levels the field. It recognizes that safety practitioners come from engineering, industrial operations, healthcare, management, and many other disciplines. There is no single starting point. So this chapter resets the foundation, ensuring that everyone, regardless of background, is equipped with the same quantitative baseline.
That framing is perfect. The source material is very clear on this. Because modern safety practitioners, you all come from such a varied landscape.
Right.
You might have a strong background in engineering or a deep history in organizational management, maybe even a clinical perspective from healthcare.
So there's no single starting point.
Exactly, which means a comprehensive brush-up on foundational math, specifically algebra, trigonometry, and some advanced functions, is, well, it's non-negotiable. These concepts underpin virtually every quantitative calculation in the field.
Everything from, ventilation flow rates?
Ventilation flow rates, statistical sampling analysis, you name it. It's all built on this.
And since we're talking about quantitative analysis, let's address the tools right away. I think that's so important. When you're preparing for a high-stakes certification, knowing your equipment is half the battle.
It really is.
So what's the most important logistical detail about the calculator you'll be using?
The most critical detail is specificity. The only calculator you will use is an on-screen emulator of the TI-30XS scientific calculator.
Okay, so not your own.
No, you can't bring your own physical calculator, and you won't be given one. So practicing specifically with that interface beforehand is it's essential for maximizing time and efficiency. You really need to build that muscle memory.
Wait, let me push back on that slightly. If I understand the core principles, how to use a tangent function or how to handle exponents, shouldn't I be able to translate that to any scientific calculator? Is the TI-30XS really that unique?
That's a fair question. It's not necessarily unique in its function, but it is unique in its operation.
Okay.
I mean, think about the difference between navigating the phone keyboard you use every single day and one you encounter, say, once a year. The TI-30XS has specific keystroke sequences for things like inverse functions, storing variables, setting the order of operations.
Little things that can trip you up.
Exactly. And under the immense pressure of an exam, fumbling to find the right key combination for, say, a sine inverse function that wastes precious minutes.
Right, the cognitive load.
Precisely. Preparation with that exact interface prevents that cognitive load, and it lets you focus purely on the problem, not the process of using the tool.
That makes perfect sense. Efficiency through familiarity is competence. And there's one other critical detail the source material gives about computational results, and it's a detail that hints at a really fascinating ethical discussion we'll save for the end.
Yes. The source explicitly notes that solutions to computational items are usually rounded.
Usually rounded.
Yeah. Your goal, especially in a multiple-choice environment, is rarely to achieve some exact, textbook-perfect result down to 10 decimal places.
Yeah.
Instead, you select the answer choice that is the closest to the computed value you reach.
So getting comfortable with close enough is part of the skill set.
It is. Understanding the role of rounding is fundamental to working in this field, and we will definitely circle back to why that matters so much in practice.
Excellent context. Okay, with that stage set, let's jump into our first major topic, which is all about making the massive manageable. We need to master the language we use for numbers that are either, astronomically huge or infinitesimally small.
The language of scale.
Exactly. Let's unpack exponents and notation.
Let's do it.
Exponents are really the foundational element of that language. They're crucial for everything from, statistical data sets to calculating chemical concentrations in air samples?
Absolutely.
So let's quickly review the 3 fundamental rules provided in the source material.
Okay, the first rule, positive exponents. That's the one everyone's familiar with. 10 squared, so 10 to the power of 2 means 10 times 10, which is 100. It's a simple way to express large numbers.
Pretty straightforward.
But the rules for 0 and negative exponents, that's where people often stumble, and they are mathematically crucial.
The 0 exponent rule, it seems almost counterintuitive until you really internalize it.
It is. The rule is absolute.
Yeah.
Any base number, when raised to the power of 0, equals 1.
Always?
Always. So 10 to the power of 0 equals 1. This often appears when you're multiplying or dividing exponents, and they just cancel each other out, resulting in a power of 0.
Right. And the second rule, negative exponents, is arguably the most important for industrial hygiene practitioners. This is what takes us into the realm of the extremely small.
Precisely. A negative exponent signifies the inverse of the number. It's essentially 1 divided by the number raised to the positive exponent.
Okay, so it's not a negative number.
Not at all. The source material uses the example of 10 to the minus 6. That represents 1 divided by 10 to the power of 6. Written out, that's 0.00000001.
So 10 to the minus 6 is 1 millionth. And that level of precision, 1 millionth, that's where our job as safety professionals really begins, isn't it?
Absolutely. Think about the concentrations we deal with for highly regulated substances like crystalline silica or lead. We're often measuring in micrograms per cubic meter, right? Where micro corresponds directly to 10 to the minus 6. If you mistakenly interpret that notation, you might miscalculate a worker's exposure by a factor of 1,000.
Wow.
And for a substance like lead, where the permissible exposure limit, the PEL, is incredibly low, understanding that 10 to the minus 6 means micro is literally the difference between safe and hazardous.
And because we're constantly dealing with 0.00000001, or on the other end, huge numbers like 8 billion, we need a streamlined language. And that's where scientific notation comes in.
Yes. Scientific notation, sometimes called standard form, it standardizes the expression of those values. It converts them into a coefficient, a number between 1 and 10, which is then multiplied by a power of 10. It just makes calculations cleaner and way easier to read.
It's about getting rid of all those zeros.
Pretty much.
Yeah.
Let's review the movement of the decimal point, because that's what dictates the exponent. If we take a big number, like 392,000,
Okay.
to get the coefficient between 1 and 10, we have to move the decimal point to the left until it sits right after the 3.
So 3.92.
Exactly. And we moved it 5 places to the left. So the expression becomes 3.92 times 10 to the 5th power. Or, on your calculator, you might see this displayed as 3.92 ESO 5.
And then going the other direction, dealing with a tiny number like 0.000432, we move the decimal point to the right this time.
We move it right, 3 places to get 4.32, and because we move the decimal to the right to generate the coefficient, the exponent is negative.
So it becomes 4.3, 2 times 10 to the negative 3.
Correct, or 4.32E03. This skill set is just. It's necessary to interpret results from any analytical lab you work with.
Now, here's the crucial process I really want to unpack. Why do we need to learn this multi-step segregation technique when we're multiplying and dividing these numbers? Why can't I just, punch the entire expression into my TI-30XS?
That's a great challenge. And while the TI-30XS is smart, learning the segregation technique is about reliability and speed under pressure. If you misplace one parenthesis or misread one negative sign in a complex chain of inputs, the entire calculation fails. By segregating, you break the calculation into 2 simple, manageable parts.
Simpler is safer.
Always. First, you disregard the exponents and just multiply or divide the coefficients, the 3.21, the 4.88, and the 5.9 in the example. Second, you solve the exponents separately, just following simple addition and subtraction rules.
Okay, so let's walk through the detailed example from the source material. We need to nail the exponent rules here. The problem is 3.21 times 10 to the 5th times 4.8 times 10 to the negative 6, all divided by 5.9 times 10 to the negative 4th.
It looks like a monster.
It does.
But step 1 is simple. Multiply 3.21 by 4.88 and then divide that result by 5.9. That gives us a clean coefficient of 2.65. So we hold that number.
Okay, coefficient is 2.65. Now, step 2, exponents. The rule is that we add the exponents in the numerator and then we subtract the exponent in the denominator.
Right, so our numerator exponents are 5 and negative 6.
5 and minus 6.
So we start with 5 plus negative 6, which simplifies to negative 1. That's the combined power from the top part of the fraction.
Okay, minus 1. Now we have to subtract the denominator's exponent, which is negative 4. So the full exponent calculation is minus 1 minus negative 4.
And here is where that attention to detail really pays off. Subtracting a negative number is the same as adding a positive number.
So minus 1 plus 4.
Which gives us a resulting exponent of 3.
Positive 3. So we combine our coefficient, the 2.65, and our new exponent, 3. The result of that whole complex calculation is 2.65 times 10 to the 3rd.
It is. And that deliberate step-by-step method is just indispensable when time is short and the pressure is on.
It feels much more reliable.
Now, we can move to a subtle but really vital distinction in how numbers are reported in the safety world. While scientific notation is mathematically elegant, the safety profession, particularly within the System International, or SI, overwhelmingly favors engineering notation.
Okay, what's the core difference? What makes engineering notation the preferred standard for safety?
The primary difference is a strict rule. The power of 10 must always be a multiple of 3.
A multiple of 3, so like 3, 6, 9, or negative 3, negative 6.
Exactly. This structure is essential because it ensures direct compatibility with the universal SI prefixes. If your exponent isn't 10 to the 3rd or 10 to the 6th, you can't use standard prefixes like kilo or mega. And that leads to reporting confusion when you're trying to communicate results globally.
So it's a structural necessity. It's to make sure everyone reading a ventilation spec sheet or a toxicology report is using the exact same language.
Precisely. The prefix is the notation. And this is a great time to dive into the table from the source material, table 5.1, because these prefixes are, well, they're the lingua franca of safety reporting.
Right.
We need to internalize these 3-step jumps.
Well, let's do it.
Okay, starting with the large scales, often used for things like data storage or facility capacities.
Yeah.
You have giga with a capital G, which is 10 to the 9th, or a billion.
Wait.
Then mega, capital M, is 10 to the 6th, or a million. Think megawatts of power, or millions of liters of containment capacity.
And kilo.
And kilo, lowercase k, is 10 to the 3rd, or 1,000. Kilograms, kilometers, that's familiar to everyone.
And as we descend the scale, we find the common measurements that impact daily field work. Now, the intermediate steps, DEPSI and CENTI, they actually break that rule of 3. But they're standardized for common measures, like liters and meters.
They are. You have DECI, which is 10 to the negative 1, or 0.1, and CENTI, 10 to the negative 2, or 0.01.
But the really crucial ones for hazard control, they get back to that power of 3 rule.
They do, and it takes us right back to our conversation on exposures. You have milli, lowercase m, which is 10 to the negative 3, or 1,000. This is pervasive milligrams per cubic meter.
MGMU, you see it everywhere.
Everywhere. Then micro, the Greek letter mu, is 10 to the negative 6, or 1/1,000,000th. As we discussed, this defines the tightest exposure limits for contaminants.
Then we get even smaller.
We do. Nano, lowercase n, is 10 to the negative 9. This is crucial for emerging risks. like engineered nanomaterials, where the concentrations are minute, but the risks are potentially very high.
And finally, pico.
Pico, lowercase p, is 10 to the negative 12. You often see that in radiation measurements or extremely sensitive chemical analysis.
The insight here is really clear then. Proficiency in these prefixes, especially milli and micro, isn't just a mathematical exercise. It's the direct link between a lab result and a compliance action.
It absolutely is.
If you mix up a milligram and a microgram, that could be an error of a factor of 1,000. That could lead to a catastrophic underestimation of risk.
You've summarized the stakes perfectly. It connects the abstraction of exponents to the reality of the PLs you have to manage every single day.
Okay, moving on from the scale of our numbers, let's get into the mechanics of actually solving problems, beginning with algebra.
Fundamentals.
At its heart, whether you're dealing with a complex statistical formula or a simple ratio, it all boils down to one thing: isolating a variable.
And the fundamental principle of algebra, and really all transposition, is that you have to maintain equality. You must perform the exact same operation on both sides of the equation.
Keep it balanced.
Always.
So let's review the mechanical process using the straightforward example from the source material. Solving for x in the equation, 6x plus 5 equals 29.
Okay. Our goal is to isolate x. So first, we have to eliminate the term that's added to 6x, which is the plus 5. To do that, we subtract 5 from both sides.
6x plus 5 minus 5 equals 29 minus 5.
Right. And that simplifies the equation down to 6x equals 24.
Okay, one step left. We have to deal with the coefficient of x. Since x is being multiplied by 6, we perform the inverse operation, which is division.
We divide both sides by 6. So 6x divided by 6 equals 24 divided by 6.
Which gives us the clean solution, x equals 4.
And while that's a simple example, it reinforces the discipline you need for transposition in more complicated multivariable equations.
And that leads us directly to transposition, which is really just applied algebra in the field. When are safety professionals most likely to be transposing a formula?
Constantly. I mean, just think about the field of ventilation. A safety manager needs to measure existing conditions and then transpose a formula to determine a required unknown variable.
Okay.
The source gives us the fundamental ventilation equation, Q equals VA.
Let's define those terms again for everyone. Q is the volumetric flow rate, the volume of air moving, often in cubic feet per minute or CFM.
Right. V is the velocity of the air, its speed in feet per minute, FPM. And A is the cross-sectional area of the duct or the opening in square feet.
Okay. Q equals VA.
Now imagine the scenario. You've measured the required volumetric flow rate, Q, that you need to capture a contaminant.
Yeah.
And you've measured the velocity, V, of the air you're pulling. But what you need to know is the minimum area, A, of the duct. You need to maintain those figures.
So you need to solve for A.
You need to transpose Q equals VA to solve for A.
Okay, so since A and V are multiplied together, we just divide both sides by V. The V cancels out on the right, and we're left with the transposed equation, A equals Q divided by V.
And this is the critical skill. The standard equation gives you the flow rate, but transposition allows you to solve for velocity or for area. It makes the equation dynamically useful for design and for troubleshooting in real time.
I like that.
It's like being able to shift the cargo around inside the formula's container to see what fits best for your problem.
That's a great analogy. Okay, so we've mastered isolating x in a linear equation, but what about those massive nonlinear relationships we deal with constantly? I'm thinking specifically about things like noise or radiation levels.
Right.
That's where we need to bring in the power of logarithms.
Logarithms are the mathematical tool built specifically to deal with those exponential relationships. A logarithm fundamentally asks the question, to what exponent must this base number be raised to get the number I'm interested in? By converting these huge exponential leaps into small linear steps, we make massive data ranges manageable.
For the safety professional, this immediately screams decibels. So why does the decibel scale rely so heavily on the specific laws of logarithms?
That's the perfect connection. The perceived loudness of sound does not increase linearly, it increases exponentially.
It's not one-to-one.
Not at all. For every doubling of sound intensity, we only see an increase of about 3 decibels. This is where the laws of logs become absolutely essential.
Okay, let's look at the first law.
The first law of logarithms states that the logarithm of multiplication is the sum of the individual logarithms. So log of x times y equals log of x plus log of y.
So multiplication turns into simple addition.
Exactly. When you are measuring sound, you're dealing with sound intensity, which is multiplied exponentially. But by applying the logarithmic scale, the decibel scale, you convert that exponential multiplication into simple linear addition.
So if you have two identical sound sources,
You don't double the decibels, you just add a small amount, typically 3 dB. This log rule is the entire reason that measurement system works. You're adding the intensity increase, but on a compressed logarithmic scale.
I see the connection there. It allows us to manage these massive differences in power using small, manageable numbers. Let's confirm the laws using the specific numbers from the source material.
Okay, so the second law deals with division. Log of x divided by y equals log of x minus log of y. So division turns into subtraction.
Simple enough. For multiplication, the source gives the example of log of 4 times 5.
Right, so following the law, we break it into log of 4 plus log of 5. The source specifies that log of 4 is 0.601 and log of 5 is 0.699.
Okay.
So adding those two together, 0.601 plus 601, we get 1.299, and that is the logarithmic value of 20. It beautifully illustrates how the rule lets us break down complex multiplication using simple addition.
And for the division example, the log of 4 divided by 5.
Following the law of division, this becomes log of 4 minus log of 5, or 0.601 minus 0.699.
Which gives a negative number.
It does. The result here is negative 0.098. Mastering these transformation laws is key to solving problems involving ratios and exponential growth, particularly something like noise dose calculations, where you have to combine different exposure levels throughout a day.
Okay, our journey now takes us from these more abstract numbers into the tangible world of geometry and force analysis, starting with trigonometry.
Right. We're moving toward concepts used in analyzing stability, forces, and spatial relationships.
Things you can see and touch.
Exactly. And trigonometry is built entirely on the relationships within a right-angle triangle. We define the three sides relative to a specific angle we care about.
Okay, what are the sides?
You have the hypotenuse, which is always the longest side, opposite the right angle. You have the opposite side, which is directly across from the angle we are analyzing. And you have the adjacent side, which is next to the angle we're analyzing.
And the most enduring memory aid from high school math is necessary here. SOHCAHTOA.
Indeed. It's unforgettable for a reason. SOHCAHTO encapsulates the three core functions we need.
So SOH.
SOH stands for sine equals opposite divided by hypotenuse.
CH.
CA is cosine equals opposite divided by hypotenuse.
And TOA.
And TOA is tangent equals opposite divided by adjacent.
Okay, let's make this immediately practical. Where does a safety professional actually use these ratios out in the field?
Oh, everywhere gravity and stability are involved. I mean, consider a really common application. Ladder safety.
Of course.
OSHA standards require that the base of a ladder be placed 1 foot away from the wall for every 4 feet of working ladder length. That's a 4-to-1 ratio. And that 4-to-1 ratio is a trigonometry problem just waiting to be solved.
A 4-to-1 ratio of height to distance. So if we treat the ground, the ladder, and the wall as a right triangle, we know the ratio of the two legs.
We do.
So which function would we use to find the angle the ladder makes with the ground?
Well, since we know the opposite side, the height on the wall, 4 units, and the adjacent side, the distance from the wall on the ground, 1 unit, we would use the tangent function.
So tangent equals opposite over adjacent.
Right, but I think I might have flipped that. Let's think. The angle is with the ground, so the height is the opposite side, and the distance along the ground is the adjacent side. So tangent is 4 divided by 1, which is 4. My apologies. Let's stick with the source materials example to be precise.
Good call.
This brings us to the next step, though, using inverse functions. If we know the ratio, the tangent, we need the inverse function to calculate the actual degree measure of the angle itself.
Right, so these are the arcsine, arcosine, and arctangent functions on your calculator. They look like sine to the -1, cosine to the -1.
Yes, sin along, cosine, tan. You usually have to hit the second or shift key to access them. So let's use the specific example from the source material, which is often used in other contexts like, say, excavation sloping. Suppose we have a scenario where the ratio of the opposite side to the adjacent side is 0.75. The tangent is 0.75.
Okay, so we would calculate the arctangent of 0.75.
Exactly. And the result is 36.87 degrees. And again, as we discussed right at the start, in practice, this value is typically rounded off for simplicity.
To 37 degrees.
The 37 degrees. So whether it's setting up an anchor point for fall protection, analyzing load forces on a structure, or ensuring a trench wall slope is stable, trigonometry is the geometric language of safety.
Okay, let's now turn to what I like to call the nuclear option of the math review. the quadratic equation.
A good name for it.
This tool only becomes necessary when you encounter those second-degree polynomial equations where the variable is squared, so you have an x squared term.
You're right to call it the nuclear option. While most field problems are linear, certain physics problems, like complex fluid dynamics, calculating the properties of a pressurized system, or dynamic force analysis, can result in a formula shaped like x plus bx plus c equals 0.
And when you hit that square term,
simple algebra won't work anymore. You need that specific quadratic formula to find the value of x.
that formula is huge. Is there any simplification or shortcut we need to know, or do we really have to just internalize every single part of it?
You have to internalize the formula completely because there are no safe shortcuts. However, understanding the parts makes it much more manageable.
Okay, what is the formula?
The formula is x equals negative b plus or minus the square root of d squared minus 4c, all of that divided by 2a.
Okay.
The beautiful thing about the source material here is that it walks through a concrete application, showing you exactly how to manage that complexity. Let's solve the problem it presents. 2x squared minus 4x minus 3.
Okay, first step is to identify the coefficients.
Right.
A, B, and C.
Yeah.
In this equation, A is 2, B is -4, and C is -3.
Now, let's insert those coefficients deliberately into the formula, being extra careful with the negative signs, particularly that very first term, negative b.
Right, so that's -4.
Yes, so x equals -4, plus or minus the square root of, in parentheses, -4 squared, minus 4 times 2 times -3, all divided by 2 times 2.
Okay, let's simplify the numerator first. -4 simplifies cleanly to +4.
It does. Now we can focus inside the square root, which is called the discriminant.
It's a discriminant.
Inside the discriminant, we have two key parts. First, -4 squared. Squaring a negative number always yields a positive, so that's +16.
Okay.
Second, we calculate the 4, a c term. 4 times 2 times -3.
4 times 2 is 8. 8 times -3 is -24.
Right. But notice we are subtracting that result in the formula. So the term under the square root becomes 16 minus -24.
There's that double negative again. So it's 16 plus 24.
Which simplifies the discriminant beautifully to the square root of 40. Meanwhile, the denominator simplifies to 2 times 2, or just 4.
So we have reduced that entire complex equation down to x equals 4 plus or minus the square root of 40, all divided by 4.
Exactly. And the square root of 40 is approximately 6.32. Now we can see why the formula has that x1, 2 notation. The plus or minus sign means there are two possible mathematical solutions for x.
Okay, so x1 would be 4 plus 6.32 divided by 4, and x2 would be 4 minus 6.32 divided by 4.
That's correct. For the first one, x1 is 10.32 divided by 4, which is 2.58.
And x2?
And x2 is -2.32 divided by 4, which is -0.58.
This raises a really important point. If we are solving a physical safety problem, say calculating the required length of a support beam or a concentration level, we have two mathematical answers, one positive and one negative.
We do.
So how does the safety professional discern which one is the real-world answer?
And that's where physics and engineering judgment have to supersede the pure math. When the problem relates to a physical quantity that cannot be negative like distance, velocity, mass, or time, the safety professional must reject the negative root.
So in this case, the negative 0.58.
You'd reject it because it's physically impossible in many contexts. The context of the safety problem dictates which mathematical solution is the correct, real-world answer. This confirms that this proficiency isn't just about calculation. It's about applied technical judgment.
It's about interpreting the numbers.
Precisely.
Okay, let's wrap this up.
We have completed a really rigorous review of the essential mathematical infrastructure provided in Chapter 5. We started with those foundational tools for managing scale, the precision required for scientific notation, and, more importantly, the crucial SI compatibility offered by engineering notation and its reliance on powers of 3.
Right. That ability to handle 10 to the -6 is just paramount for industrial hygiene.
It is. Then we covered the operational tools, the mechanical necessity of transposition in algebra, which allows us to quickly manipulate formulas like the ventilation equation QVA to solve for any unknown variable we need out in the field.
And finally, we synthesize the analytical functions.
Yes. Understanding logarithms to effectively manage those nonlinear exponential risks like noise exposure, and mastering trigonometry and the quadratic equation to solve problems related to geometry, stability, and complex physics models.
And I think it's clear that proficiency in these areas translates directly into the kind of demonstrable technical competence that really elevates the safety role beyond just administration.
I agree.
If you can perform these computations accurately and quickly, you ensure that hazard controls are based on sound, defensible data.
It's about minimizing uncertainty. And that brings us full circle back to that provocative thought we touched on right at the start, the rule about rounding.
Right. The STOSH material tell you that computational results are usually rounded, and you must select the closest answer.
For the test, yes. The goal in the exam is often to achieve the best administrative fit, the closest number.
But in the real world.
Exactly. Now consider this in the context of the field. Let's use your exposure example. You calculate an airborne concentration of crystalline silica for an employee, and the raw calculation is 49.5 micrograms per cubic meter.
Okay, 49.5.
And the established permissible exposure limit, the PEL, is 50 micrograms per cubic meter.
So mathematically, 49.5 is technically below the limit. You could round down even.
If you are calculating for a compliance report or selecting a multiple choice answer, you might just choose the closest number. But what are the ethical and professional implications when a calculation, even one slightly under the limit like 49.5, means the difference between classifying an exposure as acceptable or unacceptable?
And therefore justifying the need for mandatory respiratory protection or new engineering controls.
Precisely. The reliance on arithmetic accuracy, coupled with the inherent variability of measurement and the practice of rounding, forces the safety professional to step back. The challenge isn't just about getting the math right. It's about deciding how to apply that math to favor the highest standard of protection.
So you choose the conservative, protective answer, not merely the closest administrative fit.
That's the professional and ethical choice. This reliance on arithmetic accuracy elevates the profession's responsibility. It confirms that the underlying goal of all this math isn't just computation, it's maximizing worker safety, even when the numbers themselves are slightly ambiguous. That tension between mathematical accuracy and protective ethics is something every single safety professional has to grapple with every day.